Welcome to the session on monotone embedding and affine inversion of probability models. I'm Jun Zhang, and this is Ohara Atsumi-san. So the first talk is Doubly, autoparallel structure and its application by Atsumi Ohara.
Thank you, Jim. Sorry, but this talk may not be related to embedding or affine imagine, but anyway, so I will talk this title. And this work is partly a joint work with Professor Ishii from Nagoya University. So as you may know, I think you know well, but information geometry is a branch of differential geometry with the Riemannian metric and pair of affine connections. And it originates from probability, the geometry of geometric structure of probability density. And this geometry has many applications in several information sciences or statistical science like that. So this is a quick review of the information geometry. S is a manifold, and statistical manifold is G Riemannian metric, and a pair of two torsion-free affine connections, which satisfies this relation. Statistical manifold is defined is the manifold which satisfies this relation, and this manifold is so the either of these two questions are satisfied, then automatically the other is also satisfied. So if the R is a curvature tensor of defined by connection, two connection. So in this case, we say dual, the statistical manifold is dually fast. And we also have, this is one parameter family of connecting the primary connection and the dual connection, Laplace stars. This connection is called alpha connections. Okay. So since one of the main feature is statistical manifold has two connections, but it is restricted to satisfy this relation. But anyway, so statistical manifold has two connections. Then it would be natural to consider the structure of the submanifold M, which is autoparallel with respect to a primary connection nabla, and it is also simultaneously autoparallel to nabla star. We call such a submanifold doubly autoparallel. It means this manifold M is autoparallel with respect to both affine connections. Okay. Such a submanifold has a very interesting property. So this is equivalent properties. If submanifold M is a doubly autoparallel, then M is this is alpha connection. Two different alpha for two different alpha. The manifold is autoparallel for example, nabla alpha and nabla beta. Then it is also doubly autoparallel. And so doubly autoparallel is actually for arbitrary alpha autoparallel. Okay, and like this, all the alpha geodesics connecting two points on the submanifold M lay in a submanifold, and M is affinely constrained to both primary affine connection, coordinate of primary connection, coordinate of primary affine connections and dual affine connections. Okay, so and finally, if we consider the statistical model, then we sometimes consider the alpha projection, which is a minimizer of alpha divergence. Then, but so if M is doubly autoparallel, such a projection is always unique, independent of the parameter alpha. So there are several interesting properties, and here is the existing result. I and Professor Ishii give a characterization on the simplex, on the probability simplex. We give a characterization of doubly autoparallel manifold, submanifold, using Adamar algebra, and its classification is also given. This is, of course, the kind of space of finite distributions of set of finite, the space of distributions of finite events. And here is relevant applications. And note that the related work is also done I and his colleagues. So then the purpose of this presentation is we consider another manifold, which is called symmetric cones. And in particular, I explained applications for the real symmetric positive definite matrix denoted by PDN. This is a particular example of asymmetric cones. Okay, so symmetric cone. What is symmetric cone? Symmetric cone is in Euclidean space. V is a homogeneous space and satisfies self-dual. I will explain in detail later. And in such symmetric cones, we can define kind of this information geometry. So I will explain in detail from here. Okay. So symmetric cone is closely related to Jordan algebra. So V is a vector space, and star is an algebra. This product is commutative and satisfying required to satisfy these special strange relations, associative relations. Then anyway, so if we are given vector space V and Jordan algebra, Jordan product, commutative and satisfying this relation, then symmetric cone is defined also like this. So this is an example, well-known familiar example. When we consider the Hermite matrices, the set of Hermite matrices, then Jordan product satisfying the commutative and this relation is nothing but this kind of relation. And to the interior for this product is nothing but positive definite matrices. Okay. So on the symmetric cones, here this function is called the logarithmic characteristic function, and in matrix case, determinant in this case is determinant of the Jordan algebra. But anyway, so and this function is always strongly convex, and we consider this inner product satisfying this one. So we identify this inner product as a pairing of a dual space of V. Then dual cone omega star is defined like this. In the element S is in dual space V star, and satisfied for all x in omega except 0 is positive. Omega star, this omega star is called dual cone. Okay, let D be a canonical flat affine connection on the primal space V, and U from U1 to UN is an arbitrary set of basis vector of V, and this is a coordinate. So every element x in V can be represented like this. And since D is a canonical coordinate, so then it's equal 0. So affine coordinate. And S is a dual coordinate on B star, satisfying this relation. This is a pairing which is shown in the previous slide. And gradient map iota is defined like this. Then in the symmetric cone, Legendre transform can be represented inverse element of inverse of the element. Then okay, so then G Riemann metric G is defined Hessian of the logarithmic characteristics function phi. So this is a nothing but a Hessian structure. And the definition of the connection D prime. What is D prime? D prime is so D star is the canonical flat affine connection on the dual space of V. And the D prime is defined pullback of the D star like this.
Can you go back to say iota?
Sorry? Sorry?
The previous slide?
Previous slide? Go back.
It's lost me. Iota is defined by that Legendre transform?
Yeah, this can be regarded as a Legendre transform. So in a symmetric cone, x inverse is nothing but a Legendre transform.
Iota is defined by that?
Sorry?
The I.
Iota is defined like this. So this is from primal space to dual space. Okay. Then so the D and the D prime satisfy this relation. So we so this is a statistical manifold, and furthermore this is dually flat. Okay. So we, on the symmetrical we can introduce dually flat information geometric structure like this. Okay. And this is a simple remark. We identified the tangent vector at x and basis vector uy. Okay. So this is Professor Wohash and the result of Professor result and mine. So actually the Navier-Stokes connection, which introduced before, can be represented by Jordan product. But this is a little bit complicated. But anyway, so the tangent vector x at the point x can be represented like this symbol is defined like this. This is called a mutation of the Jordan product. So, but this is a simple case. For the positive matrix, this can be simplified like this. Okay. This is very similar to Jordan product. So anyway, dual connection on symmetric cone omega can be characterized by mutation of a Jordan product. Okay, so and this is a characterization. So a submanifold M, which is the intersection of because this requires the M is already nabla autoparallel, and so this is the submanifold M is a intersection of a affine subspace and symmetric cone omega, and if so this structure is nabla autoparallel, but if the subspace W is a Jordan subalgebra, then this submanifold in omega is a doubly autoparallel. This is one of the results, and P is not necessarily in the symmetric cone. Okay, I'll take it. But previous theorem, this is another characterization of a symmetric cone. If M is a nabla autoparallel, then P the M is represented like this, and M is nabla autoparallel. So inverse appears before. Inverse is linearly constrained like this, using some A prime and W prime. This is subspace. So this is another characterization for W autoparallel submanifold in symmetric cone. So here is a very, very interesting, simple example. So the P, if P is given like this, the P inverse is given like this. Y1 and Y2 is represented like this. This is linearly constrained, and P inverse is also linearly constrained. So this the positive definite matrices of this form is W autoparallel. Okay, now I move to application on the PDN. So note this PDN is a set of real symmetric positive matrices. And I will explain this one. I'll skip this one. The first one is MLE for linearly structured covariance matrices. If this problem we consider on the W autoparallel, to estimate this this covariance can be cast as a convex problem. And the other one, the second one is we give a formula for optimal solution for SDP. SDP is explained later. So sorry. So the first one is this is a zero mean multivariate Gaussian with a sigma is a covariance matrix. And in practice, there are often we consider M has a linearly constrained structure like this. So this is an intersection of positive definite matrices and affine structure. Here is two examples. One is a triplet structure, which appears signal processing in many ways, and zero patterns. This is very familiar in the graph. Graph estimation. And anyway, so if we consider the negative of logarithmic function, then it is calculated like this. And here minus log determinant is actually convex function. But unfortunately, here appears inverse of sigma. And this is a linear function. But here appears the sigma inverse. So if this sigma inverse and sigma is also linear structure, then the minimization of this function can be cast as a convex program. So as I said before, if M appeared here, M is a structural matrix, linearly constant structure. This is also inversely linear structure. This is nothing but doubly autoparallelism. Then the MLE can be has a unique solution because it is strongly convex and numerically tractable. Okay, I skip that. And another one is SDP. E0 EM is given the data of the optimization program, and we consider affine affinely linearly constrained structure like this, and we denote this subset L. L is already nabla autoparallel. So the semi-definite programming is described like this. Given the data E from E0 to En, M, and the C objective vector, then minimizing a linear function on the set of the intersection of a positive definite cone and affine structure L. So this has many good broad class of convex program. And to solve this optimization program, affine scaling trajectory, which is a red one, and if the one feasible point is given, then there is a homotopy path to the optimal solution here. So, and to iterating by iteration numerically to follow this red line is a typical method to solve this optimization problem. But here is a key observation 2, 3, and 3. These two. So this is first of all, affine scaling trajectory is nabla-tilde star. So nabla-tilde star is a connection on the submanifold. And so anyway, so I'm sorry. This is the definition of doubly autoparallel. And finally, doubly autoparallel. So for submanifold, the nabla star geodesics can be explicitly given like this. Using this fact, we can like this. If feasible point is feasible region is dA, then the SEV can be explicitly solved. And furthermore, the formula is given like this. So I will skip this part, but anyway, it is important. The SDP, the feasible region of SDP is doubly autoparallel. Then we can have an explicit formula for the optimal solution. Okay, thank you. This is.
Thank you very much.